Okay, so continuing with some more complex kinematics problems. This one is arguably known as complex. It depends on how you want to look at it. I remember that this being basically the form of a weird, like in TV shows, they always did this for standardized tests. You'd have two trains that were starting off at different places and moving towards each other, that sort of thing. But I found it's actually a little bit trickier than most people think about if you haven't worked with it before. In class, we actually do a lab with these where we have little cars that go at different rates, and then you all have to set up and find where they would meet starting some distance apart. But instead of just talking about cars or trains or anything like that, we're going to take a look at it a little bit differently. So we've got the following. A hurricane is moving directly to the west across the Atlantic Ocean at a speed of 25 meters per second. Okay, so that's almost 60 miles per hour. So we're going to say that our hurricane is green. Hurricane. Not drawn to scale. And it is moving to the west, so let's say to the left here, that the velocity of the hurricane is equal to, or I should say the speed anyway, is 25 meters per second. Now technically it's in the negative direction. We're going to get a little creative with our vectors on this, just so we can simplify it some. You can go through and keep track of the full vectors with their negatives and so forth, but it can be a little problematic. So, all right, it'll make a little bit more sense if we just use their magnitudes. We've also got a major thunderstorm, that is heading directly to the east towards the hurricane at 18 meters per second. So we're going to say the thunderstorm is equal to 18 meters per second. Now with these are actually the speeds, so they are the magnitudes. So one's going to the right, the way that I'm drawing it, east, and one is heading to the west, to the left. If the two weather patterns are 45 kilometers apart, so this one starts here, and we go over here, we say that they start off 45 kilometers away from each other. I have two questions. A, how long will it take until they reach one another? That's question one. What am I looking for in that? Well, in class, we talked about talking like regular people. We don't say t is equal to, we talk like regular people. So how long until they run into each other? What I'm actually asking for is, what's the time that it's going to take for them to move towards each other and then collide? All right, let's see. And how far will the thunderstorm have moved during this time? So the thunderstorm is going to move this way, and the hurricane is going to move this way, and they're going to meet somewhere in here, like this. I'm asking how far this is, delta x of the thunderstorm, you could say. Okay, great. We've also got something over here, delta x of the hurricane, just so I can draw that out. Both of them are going to do some moving. Okay. All right, they're both starting like this, and they're moving towards each other. We've got two objects that we're working with here. So one of the first things that I want to emphasize on this is let's get some kinematic variables and values for both. We're going to have, during the motion we care about, we've got delta x of the thunderstorm. We don't know what that is, but that is one of the things we're looking for. We have the initial velocity, final velocity of the thunderstorm, which I never tell you that these speed up or slow down. A lot of times with weather patterns, while they do speed up and slow down over time, we may not necessarily have that information. You can assume with this, unless I tell you otherwise, that they're going at a constant speed. I'll try and update this that it says constant speed in there. Okay, great. So our thunderstorm, we said, was going at 18 meters per second. That's going to be its initial velocity and its final velocity. There'll be a different video that I shoot that has a similar problem, except one of them is accelerating, so you can deal with accelerations. I really don't know what my board is doing, and I wish that it would stop that. Do I need to do a software update? Okay. Acceleration of the thunderstorm is going to be 0 meters per second squared, and we've got the time for the thunderstorm's motion. Then we've got another object, delta x of the hurricane. We've got the final of the hurricane, which we said was 25 meters per second. Technically negative because it's moving to the left. The initial of the hurricane is equal to also 25 meters per second. But for this, we're just going to deal with the magnitudes of them, and I'll show you how. a hurricane. Neither of them are speeding up or slowing down, at least in this problem. So we're going to go with this. And we have some time that it's moving for. Here's the problem. We have two things that we don't know, and I'm asking you for both of them. Speaking of not knowing things, bored, stop acting weird. Okay, this is all the info we've got. I want to find delta xt, how far the thunderstorm moves during all of this, and I also want to know when these two are going to collide. This is actually a complex, or a more complex problem that involves something called simultaneous equations. It means that you've got a bunch of unknowns, and the only way to move forward with them is to actually solve them both at the same time. You may have learned these in your math classes. A lot of times they'll call them systems of equations, where you have several unknowns, and they can show you different techniques for working with them. While you have many options, I'm going to show you one way of solving this. That doesn't mean it's the only way of solving it, but some ways might be a little bit easier, some of them might be harder. I will say this. I've usually found in all the physics problems that I've solved, the technique I'm going to show you usually works the best across all of them. And that's why we're going to take a look at it specifically. Okay, but first we need to set up some relationships because we've got three things that we do not know. We do not know how far the thunderstorm goes, we do not know how far the hurricane goes, and we do not know the time it takes for them to hit. But we do know one thing, the time for the thunderstorm's motion and the time for the hurricane are actually the same, because they're both, we start our stopwatch and then some time's passing, and then they run into each other here and we stop our stopwatches. It's the same time for both of them. Now that may not always be the case. In fact, in one of the other problems, we're going to deal with something where there's a delay, so their times might be different. But we do know one thing, with this problem, our times are actually the same. That's why I didn't put subscripts on them. But their displacements are not necessarily the same. In fact, I would dare say, because one of them is moving faster, neither of them are speeding up or slowing down, that they won't go the same distances because they have the same time but different speeds. Okay, so how do we do this? The thing about systems of equations are, for every unknown you have, you need that many equations. So we've got, looks like, 3 unknowns. So we're going to need to set up 3 equations. If we had different times, we would have one time here and a different time here. That'd be 4, but now we've got an equal sign here that combines those to be just one unknown. So we need 3 equations. All right, that's okay. We know that we're going to be dealing with some time in here and for our delta x. And as we've talked about in some of the other videos, while you have 3 pieces of information, if you try and solve with these, you won't get anything because there's no limitation on it. This just says that it's moving at some rate, it never speeds up or slows down, and then it ends at going that same rate. That's literally every point of its motion. So we can't tell if it's stopping here or if it's stopping over here. We need more information. All right, so here's what we're going to do. We need to set up one equation. Let's ignore our final velocity because we're going to need at least some of this, but we need the time and the displacement because those are going to be the things that limit what we've got. So here's what I'm going to do. I'm going to use the common equation that we use, which is delta x v naught times time plus 1/2 at squared. Okay, I'm going to fill these in. We've got delta x for the thunderstorm is equal to our initial velocity for the thunderstorm, which we said, speed, 18 meters per second, times our time, well, we don't know how long it's going, plus 1/2, we do know the acceleration, that's 0, times time squared, but we don't know what time is. That being said, since the acceleration is 0, this whole term disappears, and we get the following. I have one of the equations that I need. However far the thunderstorm goes, which I don't know, but I do know that it is going to be equal to 18 meters per second, our speed, times our time. This is an equation. All I need to know is the time, and then I know exactly what my displacement is, but I don't know either of them. I need one in order to find the other. That's that simultaneous equation. 2 unknowns, and I can't solve them without knowing one or the other. Okay, then we're going to look at the other object and run it through. So we've got delta x of the hurricane is equal to the initial velocity of the hurricane times time plus 1/2 at squared. Its acceleration is also 0, so we end up with delta x of the hurricane is equal to 25 meters per second times our time, but we don't know our time. That's okay. So I've got these two equations. I've got one here, and I'm going to write the other one in. Delta xh equals 25t. There's some units in there, but I'm going to be a little lazy with them, okay? Great. Our problem is we have three unknowns, t, delta xt, and delta xh. To solve systems of equations, you need as many equations as you do unknowns. I have three unknowns, but only two equations. So I need one more relationship. And that's where drawing these out becomes very important. Delta x of the thunderstorm, I don't know what that is. I also don't know what delta x of the hurricane is, but I do know that if I take both of them and add them together, they must add up to 45 kilometers. This is also why I've been using only the magnitudes. You can put that your velocity is negative 25, and you would have that your displacement for the hurricane is negative some value, but then you would have to do that 45 plus a value gets you one of the others. It gets a little bit complex. I like working with it like this where I can see it drawn out, just using the magnitudes. I know that whatever this is and whatever this is, they have to add up to be 45 kilometers so that they meet at some point in between. So here's my last equation. 45 kilometers, which is 45,000 meters, you're going to have to do a conversion in there, is equal to delta xt, however far the thunderstorm goes, plus delta xh, however far the hurricane goes. Now, if you want to do this by keeping track of the vectors, which is a good way of doing it, it gets a little more complex and you have to be extra careful with your signs. Then one of these would be a minus, because this would be a negative to get them to add together. We know that their magnitudes, the number, whatever this distance is, plus this distance, must come up to 45 kilometers. Here we go. We have three unknowns. 1, 2, 3, but now we have three equations with those unknowns. So now we can solve for this. Okay, great. So this is delta xt. It is equal to 18t. So I'm going to plug it in there. And this is delta xh, it's 25t, so I'm going to plug that in here. Here's how you work with systems of equations in physics, at least what I found to be the best way. Get one of them in terms of another. So this one is one unknown. I've gotten it equal to some stuff with one of the other unknowns, and then replace it into one of your other equations. We got 45,000 meters equals delta xt, which we said, stop that, is 18t, 18 meters per second, times our time. That's this one here, 18t going in there, plus 25t. That goes in there. This is equal to that, and this is equal to that, so we're not changing anything, we're just writing it a little differently. They're equal to each other. So 45,000 meters is equal to 18 plus 25, that'd be 43. 43 meters per second, because these have units of meters per second, times time. Okay, great. The time for them to collide, there's my calculator. The time for them to collide is 45,000 meters divided by 43 meters per second. We'll end up with this, 1,046.5, let's call it 47. We should probably call this 1,050 seconds. How long is that? Divided by 60. That's about 17 minutes. Now we've answered question 1. How long will it take for them to run into each other? Okay. Now that may seem like a very short amount of time, but they're going 45 kilometers, but 25 meters per second is it's just a little shy of 60 miles per hour. So these are going highway speeds, and they're going probably about 35-ish miles or so off the top of my head. I'm not actually doing the calculation. So it's not going to take that long for them to actually collide. Like, we're not going to be waiting weeks on this. Okay, now we've got our time, 1,047 seconds. Here's the thing about simultaneous equations. It's a lot of work to get the first one, but we usually ask you for both. I ask for the time until they hit. We've got that. I also asked how far the thunderstorm went. Well, now that we know what the time is, we saw before, stop that, really hate this. There we go. from one of our previous equations that the displacement of a thunderstorm is equal to 18 meters per second times whatever our time was, but we didn't know it at the time. We now know that it is 1,047 seconds. 18 meters per second times seconds, that leaves me with meters, so 18 times 1,047 gives me the following. The thunderstorm moves 18,850 meters, or about 18.9 kilometers. Let's do a logic check on that. That's a little less than 20 kilometers. So it goes less than halfway, because we've got a total of 45 kilometers, which is what we would expect because it's moving a little slower. Without going through and doing a whole bunch to double check it, at least it passes our initial glance. The key to simultaneous equations, I know that they can be tricky and difficult to work with, like this board, but what you want to do is get some equations where you're getting one of them in terms of other stuff and then start replacing until you get what you want. All right?